Welcome back. We'll continue with developing our finite element formulation for our linear elliptic scalar problem in 3D. Okay. As we proceed, one thing that may be of use, or one thing that may be advantageous to see, is how to interpret the basis functions that we're using. Since we're working in 3 dimensions, that actually gets a little difficult. And by interpret, I really mean something as simple as how do you visualize them. Right? Visualizing them in 3D is a little difficult because of the proliferation of dimensions. And so what I propose to do in the first few minutes now is give you the 2D case where it's actually easier to plot up these basis functions and get more insight into what they're doing. Okay, so let's look at that, right? So we're continuing with the same material, but we're just doing taking an aside, so to speak, here to hopefully enhance our insight. Okay, so the aside here is we're going to look at Lagrange polynomials Okay. In particular, we're looking at the linears, right? In 2D. All right. And so properly, rather than linears, these are really bilinears, therefore. Okay, because of 2D. All right. So in 2D, the situation would be the following. Instead of the use of my continuum potato represented by the foam football here, I will use a true 2D domain. Okay, so this is omega. We have the partition, right, into subdomains, and that is a typical subdomain. Okay. We're considering now the case where our subdomains are polyhedra, right? In particular, we're looking at, we're not looking at polyhedra, we're looking at quadrilaterals now, okay? Right, and that's a typical subdomain. Okay, so what we've done is we've partitioned omega into quadrilateral element subdomains right, and these are omega e's, right? As usual, E equals 1 to NEL, right? And everything else holds, right? So we have indeed, each of these is open, so we have omega, the closure of omega is the union over E of the omega e's and the closure of that union, okay? So we have this. So we partitioned it into quadrilateral element subdomains, and on these quadrilateral subdomains, we are going to consider the use of bilinear basis functions. So consider bilinear basis functions. Okay, the picture that we use in order to help us with the construction of these basis functions is one that continues along this theme of using using a parent subdomain from which every actual physical element is drawn. Okay, so this is omega E. And now we suppose that we can construct this from a parent subdomain, which is now a square. Okay, it's a square, and it lives in a space where the coordinates are labeled c and eta. Okay, since we are working with bilinear basis functions, or we want to work with bilinear basis functions, we have 4 nodes, of course, on the physical element, and so on the parent subdomain as well, we have 4 nodes, right? And this parent subdomain, you recall, is omega xi. All right, same notation. The points in the xi eta domain are picked essentially as before, accounting, however, for the fact that it is now a square. Okay, so this domain is again a bi-unit domain. So that says that these coordinates in terms of xi and eta are -1, -1, 1, -1, 1, 1, and 1, -1. Okay, all right. Again, we have, we number these nodes as a equals 1, 2, 3, 4. All right. Okay, and again, using notation that we've employed before, we may say that that the coordinates of node A, where of course we're employing this local numbering of nodes and therefore of degrees of freedom as well, right? Okay, so the coordinates, let's also make it clear here, the coordinates of local node A, okay, those coordinates in general can be denoted as xi A eta A. Okay, and they take on the values that we've put down here, right? -1, -1, 1, -1, and so on. Okay, in this setting then, here are our basis functions, right? I'll go to the next slide. So the basis functions are the following. Now, as before, though we know we're going to use these basis functions in the physical domain, we take advantage of this parent subdomain, this bi-unit domain, to parameterize our basis functions in terms of xi and eta. So we have here n1 xi comma eta equals 1/4 1 minus xi 1 minus eta n2 1/4 1 plus xi 1 minus eta n3 1/4 1 plus xi 1 plus eta and n4 1/4 of 1 minus xi 1 plus eta. Okay. These functions also can be constructed as you would expect using the general formula for Lagrange basis functions. Okay, and I'll put down that general formula a little later. Right? I'll give you the general formula for 3D, and then it should be clear how to simplify it to the two-dimensional case. Okay. Also, you note that a hint to how that general formula is going to be constructed is to notice that here we have again this idea of tensor product basis functions. If you look at any one of these basis functions, for instance this one, right, n1, it should be clear that it is a product of a basis function in the xi direction and in the eta direction. All right, and the factor of half times half gives us 1/4 here, right? So that tensor product idea continues. All right, these basis functions, again, we observe, given our definition of the specific coordinates of the nodal points in the parent domain, right? These basis functions also do satisfy the Kronecker delta property. So we have NA CB eta B equals delta AB, right? The Kronecker delta property with which we are by now very familiar. Also, when we sum up over all the nodes in the element, we sum up the basis functions, the result is 1 at every single point in the element, really. Okay? This has been expressed, of course, in terms of the coordinates in the parent subdomain, but then because we know that we're going to construct the mapping, by mapping the geometry also, we're using these same basis functions, right? Everything will work out. Okay, so the reason to go into all of this was to be able to sketch out these basis functions, and that's what I'm going to do now. Okay, so in order to look at them, I'm going to attempt to give you a perspective view here. Okay, so I'm drawing the parent subdomain here, but because of the attempt to present this as a perspective, it doesn't seem quite square. Okay, so that's our subdomain. Those are our coordinate directions, C and eta. Right? Our local node numbers are A equals 1, 2, 3, and 4. Okay, what I'm trying to signify here is that each of these node numbers has been written on a plane that is below the plane of the actual element itself, right, of the subdomain. All right, that is our origin. Okay, C and eta equals 0. I'm going to draw just the basis function corresponding to N4. All right, so I'll do this by changing colors here, and let's go with green. Okay, so if you evaluate N4, what you see is that at C and eta equal to -1 and 1 respectively, right, it takes on the value of 1, right, so this value is 1. Okay, so this is N4 equals 1. Okay, from there, if you stick to one of the coordinate planes, it comes straight down, right? Okay, linearly, right? So it's linear along eta as we just showed, and along C. Okay, once it reaches this far edge, the function stays 0. All right, and so as the Kronecker delta property suggests, N4 equals 0 at nodes other than node 4. Okay, now at this particular point, at the origin, it takes on the value of 1/4, right? And this can be checked by just substituting C and eta equals 0 in N4, in fact, in any one of the basis functions, right? All the basis functions evaluate to 1/4 at the origin. So it's just about that big, right? Okay, and what I'm going to try to do is suggest the shape that it has here. So it's essentially going to be a So it actually falls pretty rapidly until it gets to that 1/4, and from here it probably falls a little less rapidly. Okay? Okay, I recognize it doesn't look quite smooth, but anyway, that's just my poor ability to draw it, right? The important thing is that at this point, right, at that point, N4 equals 1/4. Okay? So this is what happens with N4. The same sort of thing can be checked with any other basis function, with N1, for instance, and it will look similar. It will have this sort of tent-like structure, right? Which attains the value of 1 at a equals 1, right, at that node, and goes down bilinearly to 0 at each of the other nodes. Okay, so this is an attempt to provide a little more insight into what is happening with these basis functions. The tent-like shape is the way to think about them, as you can imagine, this is more difficult to represent in 3D. So we just stick with the 2D representation to provide a more visual sense of what these functions are doing. All right, I think we'll just end this segment here, and when we come back, we will we will continue with the derivation of our finite dimensional weak form.